Prim's algorithm by Magnus, Jude, and Nate. What is Prim's algorithm? Prim's algorithm is a classic, greedy approach used to construct a minimum spanning tree. It works by starting at any vertex and continuously adding the smallest possible edge that connects the current tree to an unvisited node. It's efficient and widely used, especially in network design. Its time complexity depends on how we represent the graph, O n squared with an adjacency matrix, or O e log n if we use a priority queue. Example 1. Here, if we look at this graph, we will arbitrarily start at node S. Choosing the edge with the least amount of weight, we go S to B, S to B with a weight of 8. Continuing from that cycle, we go B to A with a weight of 9, A to E, 11, E to D, 3, D to C, 15, which gives us the minimum spanning tree that includes each node and has a total weight, well, that's the minimum, which is 46 in this case. Example 2. So we're going to make a minimum spanning tree that's going to start from node 1 on this graph. So from node 1, we can see, okay, what edge has the smallest weight, which is a weight 1 going to 4. So we go 1 to 4 with a weight of 1. Then we go 1 to 2 with a weight of 2, as that's the next smallest weight. 1 to 5 with a weight of 4. 2 to 3 with a weight of 3. And then 2 to 6 with a weight of 7. So this is a minimum spanning tree that includes each node and has the least amount of weight, which in this case is a total weight of 17. Why is Prim's algorithm effective and efficient? The efficiency of Prim's algorithm depends on the graph representation. So with an adjacency matrix, it takes O of n squared, which is okay for small or dense graphs. If we use a min heap and adjacency list, the performance improves to O e log n, which is much better for sparse graphs. Prims is ideal when we need to build or connect something with minimal cost, like wiring buildings, designing road networks, or even in-game development where path efficiency matters.
Moving on to the code. This first little part here, we're going to talk about how we're going to implement the first example that Magnus had shown in the video um, using a no graph library. So as we can see here, we set each node to have the nodes that they're connected to and the weights, defining the graph vertices and the edges, and then we initialize the algorithm. We create a set for visited nodes, and then we start with an empty list for our final MST, and then we set that our total weight is at 0. Next, we get the edge with the smallest weight. This whole section right here is essentially explaining how the algorithm is going to work. And then right down here at the bottom, we can see that we run it at starting at node S, like Magnus specified. And then we end up with the result of the minimum spanning tree, listing each node that is part of it with each corresponding weight, and then we are given the total weight of 46 as seen in the PowerPoint as well. And then next we have when we use the graphing library, we use network X here in Python. So of course we have to import those. We specify the edges again, and then we use Prim's algorithm via network X right here. We print the results and we ended up drawing it as well, just so we can visualize what it looks like. And we get the same result of a total weight of 46, each corresponding weight, and we can visualize it here. A non-trivial example that we used. So essentially what we did was we generated 20 unique node labels, A through T, those being the first 20 letters of the alphabet. And we initialize an undirected graph so that there's no particular direction and whatnot. And we randomly connect the nodes with random weights, essentially making the entire graph random. And then we start at a random node as well. And then from there, we build the spanning tree. Um, you add in some extra random edges to make the graph non-trivial. And once we run all that using Prim's algorithm using network X as well, we would print the edges, the total weights, and this right here is to visualize it. And we would get essentially the same result, just more nodes, more edges, and consequently more weights as well. And we would get this spanning tree. It's very chaotic. I mean, as would a 20 element um, spanning tree would. And the weight, of course, is up here as well. And yeah.